Thanks for joining today. This is a brief presentation about one of the topics relevant in the actual world and markets, the artificial intelligence. In the next 40 minutes, a small introductions about the use of the technology for troubleshooting CO2 transcritical refrigeration systems and inferring results using this innovative approach has been made. First, we are going to review some relevant information about maintenance type and how this approach has been evolving over the years in pro of anticipating to the failures and decreasing the downtime for the equipment, reducing potential food spoilage. Then, a little brief about system modeling and which points are relevant in the system diagnostics and troubleshooting. And finally, how to use and interpret the information for this kind of intelligent systems. Over the years, the maintenance has been evolving to fulfill requirements from the manufacturer. In our case, we are focused on manufacturing products, so the downtime is critical for us. First, we began with an approach about mass production. From the first industrial revolution, mass production was the main objective. So we changed equipment and components when these are run to fail, which represent an undisciplined approach, high repair cost, and intervene the system when sometimes it's too late. So changing some pieces will not solve the problem. And the maintenance side, and new equipment will work with not optimized system, reducing overall efficiency of the system. Then we move to lean manufacturing, which is a systematic approach to manufacturing and production that focus on eliminating waste and maximizing efficiency. This is more disciplined because implements scheduling, but this maintenance window can or cannot match with the failure appearing. We are trying to anticipate the failure, but we are not receiving any real-time feedback from a system. So we must trust that our maintenance windows are small enough to take advantage of the information that system is giving us, but large enough to use it in a good way for our technical resources. So don't having an overuse and resource and use our resource in collecting duplicate or irrelevant data. This is when the condition-based maintenance takes some relevance because we're trying to avoid unnecessary operations by installing sensors and systems that can bring relevant information to the table. In this approach, we have multiple sensors or maybe a sensor network that can leverage our own knowledge to see tendencies and anticipate to the failures, recommend spare parts, and improve system efficiency. Maybe also avoid some catastrophic events that can cause potential downtime before it's too late. And in the last approach is focused in seeing the system in a prescriptive way, in which every failure has a solution and the same failure can degrade another part of the system or the whole system as well. Similar to a doctor approaching an internist, seeing the system in a holistic way in which all parts can work as one. Because this is something that the refrigeration system have a high dependence between variables. It is impossible to have relevant results analyzing only the pressure or the temps or the current. So the approach must be measuring and taking all data that has been possible, and then works with an intelligent system to select and pre-process relevant data to infer the best results that can let the system to work in an efficient way that can bring peace of mind to contractors and owners, and also that is aligned with energy saving politics. It will decrease the food spoilage possibility. About money investment, when we change our point of view from and undisciplined to a more organized approach, we must invest in the instrumentation and learning process, knowing that this investment will decrease over the time, and because we are going to use the same instrumentation and knowledge instead of spending this amount or even more money in changing equipment and working with non-optimal systems. For the pre-modeling side, some information is required to estimate some behaviors for compressors and evaporation circuits. First, the RE 540 coefficients that is published by most of the manufacturers through their websites. This will help us to estimate the mass flow and current consumption. Second, the evaporator nominal capacities at such condition, and airflow drawn from the fan catalog. And the third one, the set points and hysteresis for pressures and temperatures for the evaporation and rejection sites. In this image, it is possible to appreciate where the different proofs are located to obtain temps, pressures, currents and voltages, even the activation signals from the evaporators. About some signals important to know will be the weather profile for the city in which the system is installed, because the expected energy consumption and pressure values will change according to this. The isentropic efficiency for compressors, which is a value of how close the compressor is about reaching the ideal performance without losses. And sometimes we can take this value as 70%, and the relative humidity level for the product stores in cold rooms, or even better, if we can measure with a controller or maybe a thermohydrometer. This data let us know a model for an equivalent compressor, which is kind like a equivalent compressor with modulation stage as big as the power fraction of the compressors activated in some specific time. And about the evaporation time, we can use the same reasoning to estimate the specific load request from the evaporators as such time as a fraction of the cooling capacity times the sensible heat ratio, which is the relationship between the sensible heat transfer and the total heat transfer. Finally, the idea is to obtain a result like this, a system with an equivalent compressor and equivalent evaporator per section group, with average temperatures that will help us to calculate some specific values as a total instead component by component. This let us use in the same algorithm system with 1, 2 or more compressors, instead designing a specific system or a specific algorithm for each number of compressor, and also a different algorithm for the evaporation circuits. Okay. In this context, for the artificial intelligence side, it's better to use normalized data, which is better to understand and avoid, for example, duplicate data, because some information and relationship must be obtained for different variables. For the computational side of view, data integrity is enhanced because we are making more reliable and trustworthy for decision-making processes. For example, different pressures can be compared in a certain way by scaling parameters and defining some limits. So pressure in our systems will take values from 0 to 1, and this could be enhance the data analysis and give to the intelligent system a way to learn about unnecessary inputs to try to explain to the system that this is a pressure value. Also, values from voltage and current consumption can be stored as a percentage error, so it's not dependent if your electrical installation is 220, 440 or 575. Current consumption is also a value that change over the time because we have an expected value from the calculation or the nominal plate from the compressor. So we can use the same calculation to obtain similar values. So these kind of transformations let us to analyze data as an error value. Okay, following this argument, we are going to start reviewing how pressure control works. The black line is the suction pressure for a specific suction group. So there are two zones, one of activation or where the compressors are engaged, and the other one is when the compressor when the pressure is too low, so we need to release the compressor load because the mass flow is too high according to the actual requirement. So we can have the same algorithm in the rejection side, but instead of activation compressors, we must activate fans or increase the frequency of the VFD when the pressure is too high, and do the opposite when the discharge pressure is too low. Whatever will be the combination case, we have two zones, regulation and protection, with 9 possibilities in total. Where blue area is where the regulation takes action, and it will be a normal behavior of the system that can be found. But if something is happening in the system, the point in the envelope, the actual point in the envelope, the regulation area, and the point will leave the protection the regulation area and will enter to the protection area, where our algorithm will detect the case. Those two algorithms must be executed and performed at the same time, and this is something that many motor controls can achieve. So it is our goal to teach to an intelligent system what could be the experimental factors that can bring us such conditions. For us as technician, we must know how to solve this. For example, in this case, when we have high suction and high discharge, we have experimental factors such refrigerant overload, maybe elevated ambient or engine room temperature, liquid line constraints, fan motor assembly, and maybe low evaporator capacity. As we know, most of the compressors are linked to an electrical motor to achieve his labor compression. So imbalances in the load of the electrical motor can cause some effects in the current consumption side, and maybe these imbalances in the voltage supply can cause some not desired imbalances. From our point of view, the expert technician must adjust the limits of low and high voltage and some criteria, such as NEMA recommends a 10% factor of the nominal voltage to do the protection. A similar criterion can be used to determine what it could be the minimal voltage that our motor can manage, and mark this limit as the phase loss, even if we have an electrical protection. A new limit can be set in our pre-processing algorithm. The current conditions, the current consumption limits must be adjusted as well, even though there is no absolute criteria for current consumption limits. There is another pair of variables that become handy to determine this. So imbalances for voltage and currents, which are normalized in a range of 2% for the current and 5% for the voltage. All these values must be calculated as it follows, and the idea is to obtain a percentage error for voltage, current, and imbalance. This one is talking about the COP. COP is basically, in a nutshell, is the relationship between the effect of the compressor, the cooling, and the power absorbed by the electrical motor linked to it. So in CO2 systems, at first doing our equivalent system is marked to the three different kind of compressors in our system: transcritical, subcritical, and parallel. So this pressure enthalpy diagram is an active diagram of the system. I mean, changes over the time because the temperatures are not static. So in this slide, we take something like a photo from a specific time. So we must consider actual values from different sensors installed in the system and perform some calculations. In this one, we can see some definitions for the points and some definitions for the enthalpy in the liquid line, evaporator outlet, and return gas temperature for the subcritical compressor. Now, to calculate the discharge line, we must calculate entropy for suction and make some other corrections according to the isentropic efficiency of the compressors. So in this one, it becomes handy having the temperatures and pressures for the system and submit this calculation to a software such Python that can manage complements such RefProf or CoolProf. From the ideal point of view, for the actual values are easier to calculate because pressures and temperatures are something provided in real time for any monitoring system, or even some controls can handle the historical and real data. The algorithm is performed to know the percentage error of the COP in the compressor and the evaporator. So increasing or decreasing values will help to the intelligent system to know what is going on about efficiency compared to the ideal value. About mass flow is the amount of refrigerant per unit of time. So commercial software calculates this value based on a polynomial regression in a calorimeter, but this data can be used and corrected by us to determine an average or estimated value in our system. First, we have the ARRI standard, and then we must correct this value according to the temperature and the changes of density in the suction compared to the standard. We have to remember that different levels of superheating can vary the density of the gas returned to the compressor. From the evaporator side of view, this is an approach that can be used to calculate the mass flow required, where the gain heat by the refrigerant is equivalent to the one given by the air. So the mass flow for the compressor is calculated to the ARRI standard, and by the other hand, the mass flow from the air down by or thrown by our fan, it's multiplied and has an addition with another value, which is the energy used to remove moisture. At the end, we must expect these values that Some of these values are taken by sensors and others can be estimated by the products. And the difference between the mass flow from the required from the evaporator and the compressors can give us some practical information. For example, differences in the mass flow will end in problems such as leakage, fluid back, and maybe evaporator core blocking. And by the other hand, the lack of mass flow will end in problems such inadequate heat transfer in our cold room. In this slide, you will see how the pressure behaves in the system. In theory, pressure drop in the CO2 system will only be in the high pressure valve, the HPV valve, and in the evaporation circuits. But some lines, such as the condenser or elements such filters, will have a pressure drop, something that in maintenance can result in a risky situation because of the production of dry ice, resulting in burnings and maybe some exposition to the technicians. The following two graphics will resume how an intelligent system can evaluate replacement of a filter by limitation of the pressure zone and correlate two sensors across the filter with the expected delta or temperatures according to a rule of thumb. In the case of these graphics, a pressure drop of 0.3 differential bar, which is approximately 4 psig. This line defines an equation and evaluates if the point belongs to a replacement zone. Can be done inside an algorithm. This can be extrapolated, for example, to see the different deltas that you want to evaluate in a system using the same principle. In this case, we have the delta for the evaporator, and in this case, we have a delta for the condenser or a gas cooler. It depends on the system that you are working right now. About report data and inference results, in this slide we have a real histogram of a cold room that is presented. So we have the following distribution. This is the raw data. If we compare this with the ideal behavior, we can find some difference at some bullet point, such in the average expected and how dispersed are the temps inside the cold room. About this, we can start inferring some information about this and ask some questions. So we are investing energy in achieving a lower temperature objective, or what effects should have this in our products, process, or quality control. Are we involving the all personnel in having the best practices in our cold room? Sometimes not all fault can rely on maintenance. Some of these side effects will be decreasing by involving good practices, but if we cannot measure our system, there is no way in which we can improve. In this case, for example, some statistical methods can be implemented from the quality control side or area. Nevertheless, some calculations must be done to try to predict some results. This is an approach about how to submit something like rates to our circuits, assigning more or less points when the temperature is closer to the set point. In that case, we have something similar to a heat map, and know if our circuits are reaching the temperature, how much of energy invested in the system is using in accomplish our objective, and how much energy we are invested in reaching lower temperatures that can damage our product. Even though frequency distribution will let us know some important results such mode, average, and graphically see if our temperature inside cold room are closer to our set point. It is important to not forget time series, both are important, and this can help us to identify trends, predictive modeling, and the time series can be useful for filtering data, statistical identification, and predictive modeling. Also, we can extrapolate this kind of behavior, so this analysis, to and try to understand what the failures in a specific area can be, and try to correlate this information, for example, the gas cooler normalized pressure with the ambient temperature profile. So knowing which data can be cataloged as normal according to the expert knowledge and correlate values has a highly dependence in how the system is installed, commissioning, and last but not less important, your knowledge as an expert, because you are one of the who is training the system. So the intelligent system will not replace you. It's an additional resource that works for you. Okay, but finally, these statistical measurements can help us to see data from other perspective. For example, the histogram series, correlate data from different sensors, having a better understanding of failures and correlate them with ambient temperature, and detect and look for potential and strategy for energy savings. This kind of analysis help us to analyze the level of regulation in our system. For example, a question that can be made is, are we using our system in a correct way? For example, the system is used to maintain a temperature, such an application a supermarket application, or it is used to reduce temperature levels, for example, a slaughterhouse or a meat processing plant. Whichever will be the case, this graphic will have more or less relevance to diagnose. So this behavior obtained from the statistical analysis can help us, for example, to adjust timers in the controller and know if we have insufficient modulation or defective programming, or the BFD or BSD, or compatibility errors between the compressor system selection and the process velocity. For example, if the application can be a supermarket, or maybe it's a process where we use to reduce the temperature levels in a low time. Okay, according to this graphic, this is a neural network, which is a computational model inspired by the structure and functioning of the human brain, and it consists of interconnected nodes called neurons. Each one is a neuron, organized in layers. The outputs are a combination of the inputs through different weights. So each arrow has a weight, but the out is passed to an activation function, which then is passed as input to the next layer of the network. These activation functions include no linearity, which allow complex relationship between inputs and outputs. The weights of the arrows are adjusted by the algorithm of backpropagation. So in the training stage, we adjust these weights, which objective is to reduce the error in the output of the network. So it becomes relevant to have enough data to train and test the model. So some issues that can be found in this kind of architectures, as the number of the hidden layers increases, it can become more difficult to propagate through all the layers during backpropagation. That is something that can be easily seen in this network. The deep neural networks with many hidden layers have many parameters which can make them prone to overfitting, with poor overconfidence and increased sensitivity to noise, because the artificial network has a highly affinity for the training data. And last, the training with so many layers can be computationally expensive and time consuming, especially when dealing with large datasets with a lot of data. This can make it difficult to scale or even work with larger models to use it in real-time application. With many hidden layers, it can become increasingly difficult to interpret and understand how the network is making some predictions, which can make it challenging to debug and refine the model. For our case, we are using this recurrent neural network. So this is the input-output set proposed to solve the problem. The internal layers are not shown because in this solution we deployed 100 hidden layers, and the idea is to simplify the inputs as normalized values and percentage errors, and the outputs as named indexes, as we know in the previous slides. So for training and testing our artificial network, some performance indicators are necessary to evaluate the feasibility of this implementation. First, we have the precision, which is the proportion of the correctly identified system issues or faults out of all the predicted issues. A high prediction value of the precision indicates that the model has the low rate of false positives. The second one is recall, which represents the proportion of correctly identified system issues or faults of the actual issues presented in the data. And the other one is the F1 score, which indicate a good balance between precision and recall, and it's often used when there is an imbalance between the positive and negative cases. We are using 70% of the data for training, 15% for testing, and other 15% for validation. So in this case, because of the problem, at some epoch, this artificial architecture requires to restart its memory before continuing the training. So the last parameter that we were talking is the R square, which is something that we use in the linear regression, but in the artificial neural networks architecture is using to measure how well the architecture predicts systems or parameters such as temperature, pressure, or energy consumption. After approving the architecture, which is a continuous process, looking for the best adjustment, it is possible to start submitting real data to predict what could be wrong inside our system. In this slide, we can see different probabilities of occurrence of some events based in the input information. We can see this is this event has a high probability. Also this one, the low current draw, and in this one, for example, we have a low COP at the evaporator and high COP at compressor. Maybe a high level of superheat is in the compressor. And we have, for example, something like damaged fans or motors in our evaporating circuits. So in this case also, with the diagnosis of the filters, a high pressure drop in the liquid line filter will tell us that now is necessary to change the liquid line filter. And this one, also one of the objectives of sharing this presentation is to share some of my work and encourage to all people who are seeing this about innovation and how to use their own inventiveness to solve problems in a different way. In order to capture all relevant data from the compressor for testing this algorithm, I developed this prototype. It's called the Symbionte UN, which is a non-invasive product for monitoring and protect compressors in real time with connection to the internet. If someone maybe it's interested in knowing more, you can reach me through my social media or maybe visit my website. And about the summary of this presentation, we have that the design criteria few times corresponds with the real-time conditions of the equipment. So the design and real-time environment are different. So we have to optimize our system in the field. We are trying to minimize the energy consumption while maximizing product. This is a classic problem in the game theory. And always save energy. Save energy no matter if you are in your house or in the company or with your customer. Always save energy. This is something that can be achievable even in your homes. And this is a presentation for intelligent systems, so never underestimate the empirical knowledge of your technicians. The knowledge of your technician is a good way to entrain an artificial intelligence system. And only say thank you and mention the two last bullets. The first one is data without purposes is worthless, and if you can measure it, you can improve it. That's a phrase, a catchphrase from Lord Kelvin. If you are interested in these presentations, also this is a free use presentation, and as I said, you can reach me in my social media. This is my social media, LinkedIn, the Google site, my email, and also my YouTube channel. And this is a little profile from myself. Thank you and have a good day.